Today, I feel like talking about fractals in the setting of fractals, nature. Oh, and our friend. 今天我想讲分形，而且处于分形的环境，大自然，还有我们的一些朋友。Because everything is one self. And everything is karma. And everything is fractal. 因为一切都是自己，那就是更高自己。一切都是因果，一切都是分形。With regards to everything is one self, that's capital one, capital self. I don't even need to be saying this because I'm just a part of oneself talking to another part of oneself. And no matter what any of us says or hears, oneself already knows. 关于一切都是更高自我，我连讲都不必要讲，因为就是自我的一部分跟自我的一部分讲话，而不管讲什么、听什么，自我已经知道一切。With regards to karma, so as Sadhguru teaches, karma is simply action and reaction. It's just like nature, it's objective, it's scientific. 关于因果Sadhguru 教的因果就是行动和后果。就像科学，就像大自然那么客观。And everything, this moment, the next moment, this action, this thought, or desires for the future, it's all actions. And then every reaction is all another action that leads to another reaction, kind of like the waves of water.每一个这一刻，这一刻，这一刻，每一个行动，每一个思想，甚至关于未来的愿望，都是行动。然后每一个后果都是另一个行动，产生另一个后果，产生另一个行动后果，就像水上的波一样。 And, well, in mathematical terms, we say that, well, everything is fractal. 用数学的语言，我们说一切都是分形。A lot of people studying now the use of fractals and the appearance of fractals in various, just everywhere. 很多人在研究，怎么用分形，还有分形处处都有的，出现的地方。There's a source coding, which Dr. Sam Rader, she thinks of herself not as the creator of source coding, but as the receiver of source coding. Because ultimately, all of these things were already there. And they're just manifested through us, that's all. And source coding is the appearance of fractals in psychology. 有叫 source coding， 翻译成中文，觉得就是源代码。然后这就是分形出现在心理学的领域。Dr. Sam Rader， 其实他认为他不是源代码的创始人，他更是那个就是那种允许河流的人，或者下载者，因为这一切现象都本来就存在的，但他们只是通过我们来呈现。There's people using fractals for healing and Chinese medicine and understanding the body. You can check out somatic stretch. 有人在用分形去and specifically Meredith Sands Keter. 有些人在用分形在做治疗和了解中医和身体。有一个现象叫 somatic stretch， 用中文应该是全体拉筋。尤其是 Meredith Sands Keter 做的研究。But fractals, they appear in the stock market and they definitely appear in nature. 分形它们也出现在股市，然后也非常经常出现在大自然。So what is a fractal? 那分形是什么呢？ Well, 咱们可以从最简单的分形开始。 we can start from the most simple fractal. So start with the Fibonacci sequence. Sequence is just a list of numbers. You can think of it as a function. All right. There's a lot we can learn from nature, you know. I don't have to say anything. Eh? You don't need to listen to a teacher. Because the thing about fractals is that, and the thing about karma, and the thing about we're all one, and science and nature, is that you could simply observe and you would know everything about yourself. You could also simply go within yourself and you would know everything about everything. 其实我们都可以跟大自然学很多很多。分形教导我们，其实你只需要观察，你就可以了解自己的一切。你也只需要往内求，你就可以了解所有一切的所有一切。我都不需要讲，你也都不需要找老师，你就可以知道一切。哦。It's so fun to teach math in nature. 在大自然讲数学非常非常好玩 because yeah, everything's just so natural. You never know what's going to happen. 因为一切都是那么自然的，你都不知道什么会发生。But the right thing always happens if you just let it. 但该发生的事情都会发生，只要你允许它。Pop quiz! That reminds me. 这提醒到我了。我们有一个惊喜的测验。Because just like in real life, you never know when you're gonna get a test. And similarly, you could think of anything in life as a test. 因为就像平常生活一样，你不知道你什么时候会被考验。同样，你也可以把生活中的任何事情都看待为一个考验。So, a long time ago, we talked about mathematical logic. So now, can you figure out, let's say that it's true that whatever is meant to happen, so if it is meant to happen, it will happen. Sounds reasonable, right? I think that's true. Based on my experience, it is. Okay, 所以我们老早以前讲了数学逻辑。所以现在你可不可以判断哪些是对的，哪些是不一定对的，哪些是错的？所以首先就是咱们假如这个是对的， 这个是成立的。该发生的事情就是若它该发生就会发生。觉得这个是合理的，应该是真实的，至少据我经验，这是成立的。Okay, so we know that if it's meant to happen, then it will happen. Okay, 所以我们知道，如果它该发生，它会发生。Now tell me, which of these statements is also true, and which of them are not necessarily true, and which of them are not true. OK, 现在你告诉我以下句子哪些是也是成立的，哪些是不一定成立的，哪些是不成立的。If it happens, it was meant to happen. 若它发生，那说明它是该发生的。If it doesn't happen, it wasn't meant to happen. 若它没有发生，它本来就不该发生。And if it's not meant to happen, it won't happen. 还有，要是它不该发生，它不会发生。Alright, so you can pause the video, think about it a bit. OK, 你可以暂停视频，想一想。Okay, I assume that you've come back. 现在你回来了吧？ A lot of other people or beings, ones, parts of oneself have also come back. 一大堆其他的生物，自我的各个部分也来了。OK， 听得还仔细的。You've been listening pretty well. Anyways, it's a good student. 好学生。Or are you a teacher? 还是老师？Oh, hello. 你好。Oh, okay. All right, I'll tell you the answer. 现在我来告诉你答案。Ready to listen? 可以听了吗 ？Okay, 那我开始。Then I'll start. So, we learned that the conditional statement goes if P then Q. 所以我们学到了那个原命题就是如果 P 则 Q. Here, the conditional statement is if it is meant to happen, then it will happen. So P is it is meant to happen. And Q is it will happen. 这里原命题是如果它该发生，则它会发生。所以P 就是它该发生 ，Q 就是它会发生。Okay. Yes, I would agree. You agree? Yeah. Nod your head if yes, shake your head if no. 你同意吗？要是同意，那就点头；不同意的话就摇头。Okay. So the contrapositive is if not Q, then not P. And so let's say that the conditional is true, all right? Then the contrapositive is true. So yes, it is true that if it doesn't happen, it was not meant to happen. 然后逆否命题就是若非 Q 则非 P。然后我们假设那个原命题是成立的，是对的。Okay. 那么逆否命题是成立的，是对的。所以这个是成立的。如果它没有发生，它本来就不该发生。Meanwhile, the inverse and the converse are not necessarily true. Sometimes they might be true, sometimes they might not be true, depending on the situation. But all we can say is that we can't say that they're true, that's all. Or that they're not necessarily true. So it's possible that they're not true. 然后逆命题和否命题是不一定成立的，也就是说它们有时候是成立的，有时候不是成立的，但那得看具体情况。我们唯一能够确切的说的是它们不一定成立，就是它们有可能不成立，就是我们没法说它们是成立的。And the converse is if P then Q, if Q then P. 逆命题就是若 Q 则 P. So this statement is not necessarily true. If it happens, it was meant to happen. 所以这个命题不一定是对的。如果它发生，它是该发生的。And the inverse is if not P, then not Q. 然后否命题就是如果非 P 则非 Q. So in this case, the inverse is, and it is also not necessarily true, that if it's not meant to happen, it will not happen. 所以这里的否命题是，而且 它是不一定对的。就是如果它不该发生，它不会发生。Okay, so back to fractals. Okay, 回到分形。Last time we talked about functions. So you take an input and you have an output. Input, output. And every input has either one output or no outputs. OK， 上次我们学了函数，就是有个输入，然后就会有个输出，然后每一个输入都会要么有一个输出，要么有0个输出，就是没有输出。所以你可以把这个数列看为一个函数，但它的输入就是 n。这里 n 属于那个黑板大 n， 就是不是实数集合，而是就是数数的集合，就是1、2、3、4、5、6、7、8等等等等等，也叫自然数。Okay, so you can think of a sequence. You can look at it as a function where the inputs are n, element of, this time blackboard bold, n, which is the set of natural numbers or counting numbers. That is 1, 2, 3, 4, 5, 6, etc. So the input is n, and then the output is the nth number in the sequence. 所以输入是 n， 然后输出是数列的第 n 个数字。Now the Fibonacci sequence, the first two numbers are 1 and then 1. 那这个 Fibonacci 数列，它的首个就是第一个和第二个数字是1和1。And then after that, every number in the sequence is the sum of the two previous numbers in the sequence. 在这以后，数列的每一个数字就是在它之前两个数字的和，就是加起来。So the next number in the Fibonacci sequence is 1 plus 1 equals 2. 所以接下来的数字就是1加1等于2。And then the next one is 1 plus 2 equals 3. 然后接下来就是1加2等于3。And then you can just keep going like this and you'll get the Fibonacci sequence goes 1, 1, 2, 3, 5, 8, 13, 21. 13 plus 21 is 34. Keep on going. 然后你就像这样继续，然后你就会得到 Fibonacci 数列，就是1、1、2、3、5、8、13、21、13加21是34，等等等等等。 Now, if you draw squares of side length equal to the Fibonacci numbers and put them next to each other going, let's say counterclockwise, then you'll notice that they spiral out. And if you connect the corners, you get the Fibonacci spiral. 然后你要是把方块而且每一个方块都是 Fibonacci 数字的叫什么大小。所以每一个方块它的一边的长度就是 Fibonacci 数列中的一个数字，然后你按照顺序把它们画，而且每一个挨一个，然后向逆时针的方向，你就会发现它们会产生一个spiral 怎么说？就是这种形状，就是从里面往外，螺丝缠，我也不知道，然后但 Fibonacci 的这个螺丝，它也有一个特征，就是它不只是可以往外，就是永远都在往外转，它也可以就是永远往里转，而且一直都往得更里，一直都往得更外，转无穷多次。So you'll get a spiral that spirals outward, and the thing about Fibonacci spirals is that they can spiral forever. And not only do they spiral outward, they can also spiral inward. And they can just forever spiral further inward and also further outward forever. And that appears in nature a lot. 这个在大自然出现的很多。So what is a fractal? 所以什么是分形？So mathematically speaking, if you read Richard Courant's book, What is Math? 用数学的观念，你要是读Richard Courant 写的书，什么是数学 ？By the way, Richard Courant, the New York University Department of Applied Math, so the Courant School or something, or was it Courant Institute, is named after Richard Courant. 关于 Richard Courant, 那个纽约大学应用数学系所，就是纪念他而名的Courant所。Yeah, the Courant Institute of Applied Math. Yeah, Courant 应用数学所。So he gives the definition in terms of Hausdorff dimension. but also roughly speaking that fractal is self-similar. 所以它给了具体的定义，就是关于Hausdorff 维度，但也有大概的概念，就是分形是自相似的。So you could zoom in forever, and you would still get structure and specifically the same shape overall. And you could zoom out of a fractal infinitely, and you would still get structure and specifically the overall same shape. 所以你可以拉近无穷多，然后这个分形它仍然有结构，而且它是一样的形状大概，然后你也可以往外拉无穷多，而这个分形它仍然有结构，而且是同样的形状大概。In terms of dimension, fractals are interesting because you can use like one-dimensional lines and curves to draw a fractal, and it will have dimension greater than 1, somewhere between like 1 and 2. 关于维度的话，分形有一个特征就是，你可以用一维的，比如线条、曲线，去画一个分形。然后它的这个分形的维度其实是超越一的，它是在1和2之间。For example, the Cantor set, 比如 Cantor 集合 is made by drawing just a line segment of length 1, and then you take away the middle third. And then, of all the remaining line segments, for each one of those, you take away the middle third of it. And then for all the remaining line segments, you take away the middle third. And you keep doing this. And its dimension is going to be between 0 and 1. Like, you'd think that you would get nothing eventually. Or just be left with 2/3 of nothing. Or at most that, or that at least you took away 1/3 of one thing. But you did it infinitely many times, so you'd think that you'd get down to 0, just like a dot. But actually, you're going to be left with a collection of dots, points, whose dimension is somewhere but is greater than 0. In fact, it might even be dimension 1. But either way, it's not dimension 0, and a dot is dimension 0. Oh yeah, it's specifically it's equivalent to the number of ternary numbers that are made with only, I think, 1s and 2s, or was it 0s and 2s or something? Yeah. So whatever percentage of numbers, decimal numbers, or I mean of just total ternary numbers, can be written with only like zeros and ones. Is whatever percentage of that length 1 you have remaining. Which is kind of like how the irrational numbers and the rational numbers are both separate parts of the set of real numbers, but they're both dense in the real numbers. And between every pair of rational numbers, there's infinitely many irrational numbers. But between every pair of irrational numbers, there's infinitely many rational numbers. However, the rational numbers are countably infinite, and the irrational numbers are uncountably infinite. 所以这个 Cantor 集合就是你画一个长度为1的线，然后你把它的中间的1/3去掉，然后剩下的每一条线，你把它们的中间的1/3去掉，然后你对每一个剩下的线，把中间1/3去掉，然后继续这样做。 继续，然后剩下的就是 Cantor 集合，然后它的维度真的很就是惊讶，是大于0，是在0和1之间的。但你以为就是用我们的I don't know。 直觉我们会觉得就是，这个 Cantor 集合就是你不停的在去掉，然后往往只剩下了0了吧，或者只剩下1点或者几个点，而且每一个点的维度都是0，所以你以为就是应该是不是只剩下就是0维度了？或者从另一个方面来想，哎，这个 Cantor 集合。 其实我们只去掉了1/3，但我们又去掉了1/3，而且这样做了无穷多次，所以我们至少应该去掉了1/3，所以它少于就是剩下的集合应该是少于1/3的长度，但其实它的维度，是0和1之间的，而且很可能接近1，其实它的维度是多少呢？你可以用3进制。 就是你要是把所有的3进制的数字，列出来，然后去掉所有的有2的，还是去掉所有的有1的，还是忘记，反正就是要么是去掉那些所有有0的，还是要么去掉所有有1的，要么去掉所有有2，叫什么数？反正就是这个数字，对。然后剩下的就相当于Cantor 集合。 然后这些剩下的三进制数字，对于所有的三进制的数字，就如同 Cantor 集合对于那个整个直线的比例的大小或者的长度。然后这个关系就有点像，有理数和无理数，它们正好是实数的两个分开的部分，而且它们都是在实数里面是幂的。也就是说，每两个实数就什么有理数之间有无穷多个无理数，但每两个无理数之间有无穷多个有理数。这都是你会在数学分析，就是大学数学学到的。So you'll learn all about these relations between, like, Cantor set, real numbers, or rational numbers, irrational numbers, and real numbers in mathematical analysis. So that's college math. At least that's how they taught it in China. I didn't learn any of that in the applied mathematical analysis class. I don't know whether the pure mathematical analysis classes in the US teach this, but I'm sure they do. 至少我是在中国的数学分析课学到了这一切，什么 Cantor 集合，有理数、无理数、实数、密度的这些关系。但我在应用数学的数学分析，就是在美国没学过，就是他们没教这些。但我不知道在纯数学系的数学分析课，在美国是不是教这些？我估计是的。但这些有理数和无理数，虽然它们都在实数域是幂的，但有理数是可数有限多的，而无理数是不可数，就是有理数是可数的无穷多的，然后无理数是不可数无穷多的。所以你要是从实数域去掉了所有的有理数，剩下的维度跟实数的维度一样，而有理数的维度就是0。So if you took from the real numbers, took away all the rational numbers, what you'd have left has the same dimension as all of the real numbers. Meanwhile, the rational numbers have dimension 0.所以这个 Cantor 集合，我们至少可以知道它的维度，是在这两个之间，它是在0和1之间的一个维度，可能0.1 6.3，我不知道。So the Cantor set, we know that its dimension is between these somewhere. So somewhere between 0 and 1. Maybe it's 0.6, maybe it's 0.3, but yeah, somewhere between. All right, that's all for today. 今天讲到这里。